Uh, Good evening, student. See, last class we have discussed elongation along x-axis, that is P by Q, and the contraction is what? Poisson ratio into P by Q. That means the force divided by Young's modulus. Because force is acting only on one direction along x-axis. This is extension, this is the contraction. Any extension is simultaneously accompanied by contraction also. We did the relation. The extension alpha is equal to, the extension is equal to force by Q. Then also contraction. What is the contraction is equal to sigma into alpha. Sigma into alpha. And this is how much contraction is, it has some fraction of the how much it expansion. It is a contraction is maybe half of the expansion. Suppose the expansion takes place, elongation is what, say 1 millimeter, this may be half millimeter, maybe coefficient is what, half, right, like that. Therefore how much is the expansion, that much contraction takes place. That is the relation. And here only one force is acting. And also I said it depends upon the force. Several forces are acting on the cube, how it behaves. That one we are going to discuss now. Consider the same cube, right? That is what A, B, C, D, E, F, G, H. Now this is x-axis, y-axis, and z-axis. Now I apply a force P here. Here also P along x-axis. Then what? Q along y-axis. Q along y-axis. R along z-axis. If three forces are acting, then here let us see what happens. Here when P alone acts, what is the expansion? This is alpha force. But here there is a contraction also takes place. Contraction along which one? Contraction along, so assume that P is at 10 Newton, right? Q is what? Say 6 Newton, R is 3 Newton, like that. Then what? There is a contraction takes place, right? Contraction takes place, expansion along, extension along x-axis, contraction along y-axis, and contraction along z-axis also. I will show how it looks.
Material property because it gives us key information about how different materials deform under loading. Let's get right into it. We can start with a quick example, the rubber band. If you take a rubber band and stretch it along its length will obviously increase, but it is also quite intuitive that at the same time, the band will get thinner. Poisson's ratio can tell us how much thinner the band is going to get. What about for a generic lump of material? Take this little orange cuboid. If we apply a compressive force to it, it will expand in the directions which are perpendicular to the direction in which we are applying the load. We call the direction along which the load is applied the longitudinal direction, and we call the perpendicular directions the lateral directions. If we reverse the direction of the force to apply a tensile load, the cuboid will obviously extend in the longitudinal direction, and it will contract in the lateral directions. The key concept here is that when you apply a load to a material in one direction, the material will also deform in the lateral directions. Poisson's ratio is the parameter that tells us how much the material will deform in the lateral directions. To define Poisson's ratio more precisely, let's take a closer look at the case where a tensile force is applied. First, let's give names to the various parameters involved. Lx, Ly, and Lz are the original dimensions of our cuboid along the x, y, and z axes. Delta Lx, delta Ly, and delta Lz are the changes in these dimensions after the load has been applied. They are shown as being divided by 2 because the change in dimension occurs on both sides of the object. Next, we can write out the strains in all three directions. As a quick reminder, strain is a measure of deformation, and is defined as the change in length divided by the original length. It is denoted using the Greek letter epsilon and is usually expressed as a percentage. When we apply our longitudinal load, it turns out that the resulting strains in the lateral directions are equal. And here's the interesting part. They are proportional to the strain in the longitudinal direction. The ratio between the longitudinal strain and the lateral strain is actually a material constant. You might have guessed it by now, but we denote this material constant with the Greek letter nu, and we call it Poisson's ratio. By the way, Poisson's ratio is named after this guy, Simeon Denis Poisson, the famous French mathematician who formally defined the ratio in a note published in 1827. Strains are negative. The minus sign is just there so that for the typical case where the lateral strains are opposite in sign to the longitudinal strains, we get a positive Poisson's ratio. Now, in this case, we can't just use Hooke's law to determine the strain in the x direction, because it will also be affected by the strains in the y and z directions. The simple version of Hooke's law for uniaxial stress no longer applies, because the strains in one direction will depend on the stresses applied in all three directions. We can use Hooke's law in combination with the equation for Poisson's ratio and the principle of superposition to obtain the equation for strain in the x direction. We can rearrange this equation into a more practical form, like so, and then apply the same process to obtain equations for strains in the y and z directions. These equations form what is known as the generalized Hooke's law and can be used to determine deformations for a case of
See, now you have an idea after seeing that particular clip or movies where how it looks. Here, very difficult to draw the diagram here, but if you see the picture, you can understand what exactly is that, what is happening. Now, what happens when I apply a force in this direction, right? That only I am going to do this now. They may ask you the question. Three forces P, Q, R, they are not equal, acting along a unit cube on a elastic material. It's an elastic material. Prove that net elongation along x-axis. Net along x-axis is equal to this one. P by Q minus sigma Q by this one. Or else they'll ask you this, right? Or you can take this common factor, and this also a common factor. This is along x-axis. What is the expansion along x-axis? Similarly on y-axis or z-axis. This is called generalized Hooke's law. Right? This only I am going to prove now. Next I am going to assume that if all forces are equal, what happens? P equal to Q is equal to R. What will happen? How it expands like a balloon, because when you inflate the deflate or inflate the balloon, forces inside the balloon acts in all direction. Either it expand or contract. It will be in that case, like, right? And prove that what alpha x, that is what expansion along any this net elongation along any axis is equal to P by Q 1 minus 2 sigma. You prove that. And also they may ask you what is the increase in volume or change in volume. See, this is the original length. When there is an elongation, what in all direction, the length increases, the volume also increases. Original volume is V1, final volume is V2. Change in volume, prove that is equal to 3. See, only difference is you are going to add 3 here. All these things you are going to do that. That is why, see, in the examination what you write for the derivation, you already done the derivation half of it, right? Then this is the continuation. Look, consider a solid cube of unit side of length, breadth, height, all are unity. Okay, let P, Q, R be the forces acting along the parallel to the x-axis, y-axis and z-axis. P, Q, R is acting. And the force P acting along x-axis produces elongation along P and also produces contraction, right? Contraction, right? These all are the contraction. This is Q and R. I'll write it simultaneously, right? If Q is the Young's modulus, then what? Longitudinal stress is equal to force per unit area, P by area. P divided by area is 1, is it not? Length into breadth. That is what 1 area. That is equal to P, which we have done already. Then longitudinal strain is what? Increase in length by original length. Increase in length is delta L by L. That is what? Alpha. Actually, do you remember this? In the cube we have done, this is alpha by 2, alpha by 2. Alpha by 2, alpha by 2 is what? Alpha. Right? That we have done. Therefore, what? Young's modulus is stress by strain, longitudinal stress by longitudinal. Stress, what you got it? Longitudinal stress. Stress is P only. Strain is alpha itself. Alpha is equal to P by Q. Therefore, this we have done. Then next again what? Poisson ratio. Contraction by extension. Contraction strain by extension strain. Contraction strain by extension. Contraction strain beta. See, do you remember? This is a contraction. This is an extension. Beta. Then what? Cross multiply. You get this. Where alpha is equal to P by Q. This is a contraction. In general, contraction is equal to sigma force by Young's modulus. The net elongation along x-axis is equal to alpha minus beta, that is contraction along y direction and contraction along z direction. That is elongation along x-axis, contraction along y-axis, contraction along z-axis. Therefore, then you know how to write it. Alpha. Beta Q means what? Sigma, what is this? Force divided by Q. Here also what? Force divided by Q. What is the force here? Along z-axis R. Along y-axis Q. Then what? Q you take as a common factor here. I have taken Q as a common factor. And this minus sigma you take common factor. You got it. This is an equation. Similarly, the net elongation along y-axis and z-axis is what? Y and z. Wherever P replace Q, wherever Q replace R. And once you write P here, Q and R is there. If Q, P and R. If it is R, P and Q. Like that. You understood? Therefore, you get all this net elongation along this one. This is the case. This is also called generalized Hooke's law. Right? Now, case if P equal to Q is equal to R, what happens? Then net elongation along each axis. What is the net along each axis? You put it here. P equal to, you take this one. Right? If P equal to Q equal to R, this is also P. This is also P. This is also P. P plus P, 2P. This P here what? Here P minus sigma 2P. P get, there is a common factor, you take it out. Therefore, you get out P by Q 1 minus 2 sigma. That only we are going to get it here, right? See. P2P, that is equal to 1 by Q P minus 2P sigma. P just to take it out, common factor. This is a net elongation. Net elongation is what? P by Q is nothing but alpha 1 minus 2 sigma, or alpha is again replace it. Then here you have finished this problem now. Net elongation. What is the net elongation? You have proved it. Over. Now 3/4 of the derivation, that means 50% of the derivation only are done. Okay. Now they may ask, prove that change in increase in volume is this. What increase in volume? In the examination, you need not prove that, directly you can write. We know that, even if we don't know, you write it. We know that change in volume is this. I'll tell you how you are getting that one, change in volume. That I added as a problem here. Look, some students, they want to know how you got it. That only I have done here. See. This is a problem. Change in volume. Change in volume means increase in volume. Prove that increase in volume, this is going to be the problem now. Right? What is the initial length? Initial length is L1. L1 is L. L is equal to 1 unit. Increase in length is what? L2. L2 is what? Original length plus net elongation. What is the net elongation you have done just now? The net elongation is this, isn't it? Net elongation is what? Alpha 1 plus 2 sigma. Alpha plus. This is the final length. Original length is L1. Final length is L2. What is the initial volume? What is the original volume? V1. That is L1 cube. That is L1 cube is L. That is 1 on DL direct. What is V2? V2 is what? L2 cube. L2 cube is this. See how to cube this. This is the problem. Let 1 minus 2 sigma is equal to B. I will put it for your convenience. Alpha is equal to P by Q. Look. Alpha is equal to P by Q. Q is Young's modulus. Its Young's modulus is about 9 into or 19 into 10 to the power of 10. It comes in the denominator. Force may be 10 Newton or 20 Newtons, something this sort, right? 20 Newton. This is 10 to the power of minus 10, right? This goes up 10 to the power. Alpha is very, very small. 10 to the power of minus 10 means what? Very small value. Therefore, alpha square is tends to 0. Alpha cube is that also tends to 0. When alpha is very, very small, then alpha cube is also tends. Therefore, here I am going to expand. This is, I will put it in a small number, right? This is alpha, this is B for convenient, right? What will if you expand is what? You know this formula, A plus B whole cube formula, A cube plus B cube plus 3AB, A plus B, isn't it? A cube plus B cube plus 3AB, A plus B. L1 cube is V1. See, L1 cube is what? Initial volume. What is L1? V1. Initial volume. This is alpha cube is what? Small 0. This is 10 to 0. Right? This is L1 is 1. Alpha, beta, this one. Then again what? This becomes 0. You bring this V1. V2 minus V1 is change in volume or increasing volume. This becomes 0. Then 3 alpha, beta. If you multiply this again what? 3 alpha, beta into 1. This one will get it. But this is what? Alpha square. Again alpha square is 0. Tends to 0. Therefore, our change in volume 3 alpha, beta. Alpha B. But B is what? 1 minus 2 sigma. Therefore, what? Increase in volume or change in volume. This you got it. Now, why I use this? See, I used to write bulk modulus everywhere K, K, K. Look, they ask you, what is the bulk modulus? Bulk modulus is equal to strain, volume strain by volume stress. What is volume stress? Volume stress strain is, sorry. Bulk modulus is equal to volume stress by volume strain. I think I am taking a lot of strain. That is the reason reversed. Volume stress but volume strain. Stress is what? Force per unit area. Strain is what? Increase in volume by original volume. Original volume. What is force per unit area? Force is P, area is 1. Increase in volume delta V by original volume 1. Therefore, as a result, what you get here? K is equal to P by change in volume. Now, change in volume, what you got it? Change in volume is how much? P. Change in volume is 3P by Q 1 minus 2 sigma. Right, PP get cancelled. Therefore, bulk modulus is equal to this. Q goes up by 3 1 minus 2 sigma. Now, in the examination, they'll ask you for 6 mark. Prove the relation between the Young's modulus and Poisson ratio and bulk modulus. That time, how you have to start? You have to start from the beginning. How? Consider the cube all that. You write the diagram, right? Get this relation, this description, you do it, the description. Then write down this fully. And change in volume, you need not show all that. All these things you can write. We know change in volume, you can come to this. You need not write all that, right? Directly change in volume is equal to this. We know that like that directly connect. You did not in the examination, you need not show all this. This is for only students want to, right? Change in volume. Then after that you start working it out step by step, right? I will do in that one in the next class. How to do for 6 marks if they ask you from the beginning, right? Okay. Anyway, now this is elasticity, the 9th video. I'm sending it, and I'm sending the what is that material also. See, now you do one thing. I'll write in the order, same the order. I'll put in the same order. How to do this? What is the class? Whatever the class I today have done, that you take it in the same order. Please possibly take the screenshot. See, whatever the notes I have taken, I am writing is, but here our HOD Dr. Govind and Dr. Suresh KSS, Dr. ASG, they have written the notes. In fact, I am discussing through that notes also. I am going through the textbook and their notes. They have written some printed notes also. Whatever the things they done in a previous year, and everything is a compilation of this. In case if you get the if you happens to read any other textbook also, you can understand how is that. Therefore, you can ask the doubts with any of our teachers. Even it is not necessary that you have to ask only me. Whoever the teacher are there, they will clearly explain. But go through all that, and writing in examination is an art. How much you have to see, this is written in an exhaustive way, and as far my knowledge concerned, I explained there may be a lot of mistakes here and there. Therefore, don't think that I'm only the ideal person to for this. Go through different notes, go to come to the department, discuss with other teachers. If you find any mistake, please correct it and send through the comments. All right, each one teach one is the right method in the world. Okay, any suggestion, please tell me. Thank you.